welcome back. So now we're going to learn how to calculate the heat needed for a phase change. And here again we see the heating curve of water. Okay, and we're going to talk about the equations that you need to use to calculate the heat as you pass through each line. So once again we have line segment A. Okay, and well, the temperature is going up, so then you're going to use the equation Q equals MC change in T. Okay, but you need to make sure you use the specific heat, okay, of water as a solid, because that's a solid point. That's with solid at that point. So at line segment B, okay, that's when it begins to turn into a liquid or it begins to melt. All the heat is going into moving the particles further apart or breaking the hydrogen bonds. And the temperature is not changing, so you're going to use this equation. Q equals MHF, okay, where F, or HF, is the heat of fusion, and you can multiply the heat of fusion times the mass. And we're going to see when we do the calculations, the units are super important. Let me do this. Okay, so for line segment C, okay, the temperature is going up again, okay, so liquid that's moving faster, we're going to use Q equals MC change in T, okay. We want to make sure we use the specific heat of water when it's in its liquid form. Okay, then for D, okay, that's when it's turning into a gas, okay, so the heat is going into moving the particles further apart. We're going to use Q equals MHV, okay, where V is the heat of vaporization. And then last but not least, see up here we have line E. Okay, they were going in to heat the particles of a gas faster. Okay, so we want to use the equation Q equals MC change in T. Okay, again, but we want to make sure this time that we're using the specific heat for water in the gas. Okay, so we're going to do two of these problems. Once you sort of get the hang of them, they're not that bad. Okay, so we're going to go to the next page, which has an example problem and has the steps to do it. Okay, so it says calculate the joules of heat needed to change 20 grams of water at 5 degrees Celsius to a liquid at 60 degrees Celsius. And just to let you know, I want to change this in terms of sig figs to this. Doing it with one sig fig is very awful. Okay, so we notice we have all this information. We're not going to need to use all of it, okay? But we're going to use some of it. So it says step 1, which we're going to do is sketch a heating curve. So if we have our little, I need to make it a little bit larger. So we have our graph. You know, a heating curve looks like this. And the important points on the curve, water is 0. So this is where melting happens. And this is where boiling happens, where it goes flat. Okay, it says so we just sketched the heating curve. That's a wonderful sketch. Okay, then it says, mark the points on the curve mentioned in the equation, or in the question. It should be the question. Can't type it. So we have water at 5 degrees Celsius. So that's about here. Merry Christmas. And then liquid at 60 degrees Celsius, which, I don't know, 60 is about here. And if we look, that's 3 line segments. I'm going to name this line segment AB. Then we're going from B to C, and then C to D. Okay, so that's how we sketch sort of where we are on the heating curve. So now I need to calculate the heat, okay, for line segment AB. Okay, and that's when the line is going up. So we're going to use the mass times the specific heat times the change in temp. Okay. And if we look, the mass of the problem, the mass of the water is 20. Now we want to use the specific heat of water when it's a solid, or when it's ice, which notice is lower. All right. So 2.06 for the specific heat. And the change in temp. Okay, so it was -5 here, and it's going to 0. So the change in temp is 5. And if I multiply those two together, which I did already, I get 206 joules as my final answer for the line segment AB. Okay, now for BC, we have to do a little bit of work. Okay, because you'll notice, so this is when it's turning into a liquid, but you'll notice the heat of fusion is given in kilojoules per mole. And our specific heat, right, our specific heat is given in joules per gram. Okay, so we need to convert, okay, the heat of fusion, okay, to joules per gram. Okay, we want to match our specific heat. Okay, so I'm actually going to scroll down and do this down here. So this is line segment BC. Okay, and I just have to go back up and look because I forgot. So the molar heat of fusion, okay, is 6.02, okay, kilojoules per mole. Okay, we need to convert that, okay, to joules per gram. Okay, well, we know that 1 mole of water is equal to 18.06 grams. This is the molar mass. That's going to make the moles cancel, and we'll be left with grams. When you do this, okay, you get 334.34, sorry, 0.334. Okay, and I'm going to keep the sig figs the same. We started with 3 sig figs, so I'm going to keep the same sig figs. Okay, so this is kilojoules per gram. But we don't want kilojoules, okay? We want joules. And to convert from kilojoules to joules, you move the decimal place 3 places. So this is 334 joules per gram. Okay. You are going to be doing the kilojoules to joule gram conversion so much. Just like the milliliters to liters conversion, that's sort of going to be the same. The kilojoules to joules conversion is going to be done a lot. Now we're ready to use that number. So remember, we're calculating the heat from B to C. And the formula that we use there, since the temperature is not changing, is the mass times the heat of fusion, which we just got in the right units right here. So our mass is still 20 times the heat of fusion, which is 334. And if we do that math out, we get 6,680 joules. Okay, and then, but now last we have to do line segment CD over there, which again, the temperature is going up. So we're going to use our, this is CD, we're going to use our MC change in T, for a line to make this neater. So our mass is still 20 now. Here we're in the liquid form. Okay, so we want to make sure that we use the specific heat of water in the liquid form, which again, if we look up here, and I gave it in more decimal places, we're just going to use the decimal places that they gave us right here, even though the AP exam is going to use 4.18. You know what? We'll just use 4.18, even though I gave it with more decimal places. So 4.18. Now we got to get our change in temp. So we're going from C to D. So from C to D, we're going from 0. And if you look in the question, this was 60. So that's a change in temperature of 60 degrees. We multiply those together. And we get 5,280. Now, what you simply have to do is take all your heats that you got, so we got one here, and one here, and add them all together. So we're going to add, okay? And when you add them all together, as we add heat, when we add all the heats together, we're going to get 11,906.8 joules. And with sig figs, it's 3, because all the numbers have 3. So with sig figs, it would be this many joules. Problem is done. Okay, we're now going to do actually one more problem, which is actually shorter, but it's not with water, so it may be a little bit more cryptic. Okay, so it says determine the heat needed to completely vaporize 100 grams of liquid ethanol, which is alcohol. All our problems are about alcohol or water, it seems. And I should have told you that, just to make this easier, that this is the formula for ethanol. Of course, I would know that, and this is its molar mass. Okay, so it's the first thing we got to do is sketch a heating curve. So here's our little heating curve. It always goes up like this. Okay, the important temperatures on the gas, the melting point on the graph are negative 11.3. That's the melting point. And the boiling point is 78.3. So those are the important temperatures. And we're starting at, so we're determining the heating to utilize 50, completely vaporize 50 grams of liquid ethanol at 21. So 21 is like around here. And somewhere in here. I did not change color. So 21, so that's somewhere between there, doesn't matter where on the graph. And we want it to be completely vaporized. So the point where it's completely vaporized or completely turned into gas is at the end of when it starts turning into a gas, which is right there. So here we have 2 line segments. We'll call this A, B, and then C. So we have to calculate 2 line segments. The heat to go from A to B, and then the heat to go from B to C. Okay, now, it's important that completely vaporized means, that's sort of the hard part here, is sort of the point at the end of when it stops being flat, because that's when it's completely turned into a gas. Okay, so from AB, the line is going up, so we're going to use Q equals MC change in T. Okay, our mass is 50. Now we want to think about what form it is here. Well, here, okay, the ethanol is a liquid, so we're going to use the specific heat capacity for a liquid, which is 2.46. And we got to get the change in temp. So at point A, it was 21, and then it's going to where it's going to start to boil. So that's 78.3. We subtract those two, and we get 57.3. And then we do the multiplying, and Q equals 7,047.9 joules. Okay, so that's for AB. Okay, I'm now going to do the same thing for BC. Again, that's when it's turning into a gas. Now again, I got to do that conversion. So if we look up here, they give us the molar heat of fusion, but it's in kilojoules per mole, and we need to convert it to joules per gram. Okay, so we have 7.61, okay, kilojoules per mole. Okay, and we know, because I told you that 1 mole of ethanol is equal to 46.07 grams. If we convert that, we do that conversion, we get 0.564, keep the sig figs the same, and this is kilojoules per gram. We want to get it into joules per gram, so we move the decimal place 3 places, and we get 564 joules per gram. Okay, now we're turning this into a gas, so we use Q equals mHV, the heat of vaporization. So our mass, I believe, was 50, and we just got our nice heat of vaporization. And 64 does not look like a 6. And then we multiply those together, and we get 200. I can't say numbers. Get that. And then again, once you calculate the two heats along the line segments, however many lines there are, you add them together. So we're going to add these two. So add. And if we add them together, we get 35,247.9. And again, usually 3 sig figs, and I think I'm just going to make the rule 3 sig figs here because I'm sick of the sig figs. So we get the sig figs, so it would be this, joules, as our final answer. And that's not a decimal, that's just the 5 sticking out. Okay, so for homework, there are 2 of these to do, okay, just like there were 2 here. And then there's some review of what we did last week with specific heat. I hope everyone had a good break. I will see you on Monday.